Welcome to the first lecture in Unit 5. It's titled, It's Not Hoarding. I'm positive I've lost an electron. I better keep an eye on that. And so what we're going to do in this lecture is we're going to first learn how to construct electron dot diagrams for elements. Secondly, we're going to understand the reason for ion formation. And then thirdly, we're going to predict the stable form of ions. And lastly, we're going to understand the formation of ionic bonds and resulting properties. So what we already know, electrons determine the reactivity. And so we know that the valence electrons in an atom make up the element or the electrons that are going to react with other things, and depending on their structure and how many they have will depend on the reactivity of that element. Atoms in a noble gas column will not react. And what we learned in the lab, so ionic substances have very high melting points, they have very high crystalline structures, and they conduct electricity very well. Now, the octet rule. We've talked about this before, but we're going to go into a little bit more detail. Atoms are most stable with filled orbital shells. So elements with the atomic number less than 36 follow the octet rule. And in general, this is what we stick to in this class. We're usually dealing with elements less than 36 electrons, or atomic number less than 36, and they follow the octet rule. Exceptions to this are hydrogen and helium. They kind of follow what they call a duet rule because they are stable with only 2 electrons. And so what stability means, being stable, is essentially having the correct number of electrons in the outer shell, the correct number of valence electrons. So Lewis electron dot diagrams, what they represent, chemists are often interested in the valence electron structure because remember, the valence electron structure tells us the reactivity of an element. Now, the valence electrons are represented as dots around the chemical symbol. And electrons are filled according to the Hund's rule. So they fill in order just like the Hund's rule, and the Hund's rule states that every orbital will get, or every arm of an orbital will get 1 electron before it gets 2. And we can see that lithium has 1 valence electron, so therefore it has 1 dot. Beryllium has 2, so it has 2 dots, and so on. So the first question we have, it says draw the Lewis dot structure for selenium. And selenium has 6 valence electrons because it is in group 16. And so what we do is we just write the symbol for selenium, and then what we will do is we will fill the electrons, or the valence electrons, around that symbol. In general speaking, most of the time we just start by filling 1, 2, 3, 4, 5, 6, and we get a shape like this. If we're being more specific, we can look at selenium. And in selenium, since it's going to have 6 valence electrons, it will end with a S2 and then a P4. And so if we're looking at an orbital notation of S2P4, we have 1, 2, 3 for P. We'll have 1, 2, and then 1, 2, 3, and 4. So in filling this, if we want to really follow the Hund's rule, what we'll do is we'll fill the S first, so 1, 2, and then fill the P, 1, 2, 3, 4. It essentially gives us the same exact Lewis dot structure, or the looking at the valence electrons, but depending on how we're being specific, will depend on how we fill. In general, this is filling all the way around and making sure that each side gets 1 before it gets 2. That's going to give you your best bet. So let's look at another one. It says proficient. A2, it says a new element is discovered with the Lewis dot structure of, we see this, what chemical family does this element belong to? And so we'll just count the valence electrons here. 2, 4, 5, 6. So we have 6. So it's going to belong to group 16 because it has 6 valence electrons, and so therefore it'll belong in that oxygen family. Now, in looking at the noble gases, or group 18, the noble gases satisfy the octet rule. The reason why they do this is because they have an effective nuclear charge of essentially 8. And when we're looking at this, it has 8 valence electrons, and it has those 8 protons pulling on those 8 valence electrons. And this is a max value of what it can have. It has 8, so therefore it's stable. It doesn't want to react with anything else, and it doesn't want to form bonds with anything else because it already has everything that it already needs. So when we look at other groups on the periodic table, essentially that everything is trying to become a noble gas. And so what we can look at this, if we look at our alkali metals, which is that's group 1 right here, they really have, initially they have an effective nuclear charge of 1. And what they have a choice is they can either gain 7 electrons or they can lose 1 electron. And by doing this, they'll get us a max value of 8. And we can take, for instance, we can take sodium and look at its valence, or look at its electron configuration, which if we look at its electron configuration, it's 1s2, 2s2, 2p6, 3s1. And so it has an option. And we're looking at that, if it loses 1 electron, essentially it has this electron structure, which that will be our neon. Or it can have the option of adding 7. And so if it adds 7, you can think that it'd be 3s2 and then 3p6. And then that would have the structure of argon. Now, what's more likely going to happen? Is it easier to lose 1 or gain 7? And obviously it's easier to lose 1 than it is to gain 7. And so that's why our group, or column 1, the alkali metals, will have a +1 oxidation number, because it generally gives up 1 electron. So its most stable state will be +1. If we look at the alkaline earth metals, well, it's just 1 column over, and we see initially it starts at 2, but see that it has an option to get 8. We can either lose 2 or gain 6. And obviously the best bet here, or the easiest thing for it to do, is going to be able to lose 2. That's why group 2 has a +2 oxidation number to get to this effective nuclear charge of 8. We're looking at the chalcogens. When we're looking at this, the oxygen family has an effective nuclear charge of 6. And you can kind of see we went from 1, 2, and we skipped all of these transition metals, and we really essentially skipped a lot of things. The reason why, when we're looking at it, the transition metals, we're not going to bother with them learning and memorizing, because their oxidation numbers change. It changes throughout, and so they can have very different forms. So the ones that we're going to memorize are going to be the ones that stay the same. So we're looking at group 16, we see it's 6, so it can either gain 2 or lose 6. What is it more likely to do? Gain 2. And so if it gains 2 negative things, it's going to have a -2 charge. And we keep going with the halogens. We see that it starts initially with 7, and so it can gain 1 or lose 7 to get to that magical number of 8, and so therefore it's more likely going to gain 1, which if it gains an electron, gains a negative, it becomes -1 for its oxidation number. And we can see that when we're doing this, we're either gaining or losing electrons, and we're either becoming a cation or an anion. Now, what a cation is, those are going to be groups 1 and 2 and group 13. Not 3, but group 13. They are more stable with less electrons, and so therefore if you lose a negative, you become more positive. And you can think cations has a T in it. A T is positive, and so cations become positive. So lithium is more stable. A lithium ion, a lithium cation, is more stable than just a lithium atom by itself. And we can look at this as an example. We see that we have lithium. If it loses this electron, its outer shell is completely filled. And you can kind of look at that and go, well, that's only 2. Well, remember that this is the first energy level, and the first energy level is only the s orbital, so therefore 2 is the max that it can have. So this max shell is what it wants, and so therefore we lose this electron. It's more stable when it has that +1 charge. Now, anions, on the other hand, that is groups 15, 16, 17. Atoms are more stable stable with more electrons. And that's why when we look at fluorine, fluorine has a -1 charge. That's more stable than just a fluorine atom that is not ionized. And so when we're looking at this, if we add an electron to it, we see that our outer shell becomes full. And when the outer shell becomes full, we have 8 valence electrons. That is where it's in its most stable form. So when we look at the periodic table, and this is something that we need to write down and make sure that we memorize it, make sure that we have. These are the ionic charges on a periodic table. So group 1 will have a +1, 2 will be +2, 13 will be +3. 14, since they're right in the middle, they can go either way. Is it easier to lose 4 or gain 4? Well, it can go either way, so therefore it can be plus or -4. And then group 15 is -3, 16 is -2, 17 is -1. And we see that the oxidation number, or the charge for the noble gases, is just 0 because it's not going to do anything. And then these transition metals, they have different charges, so therefore we don't memorize these. But these that we have here for groups 1, 2, 13, 14, 15, 16, 17, we need to have those memorized because we will use them often. So let's jump into an example. So when we're looking at this, it says how many valence electrons does a stable sulfur anion have? And this is stable is a keyword here. Anion is a keyword, and we're looking at sulfur. Now, since it's an anion, we know that it's going to be negative. We see that it's an anion. You can think anion has an N means negative. And so when we're looking at this, we're going to have a negative charge. And in that negative charge, it wants to be stable. So sulfur, when is it stable? Stable when it has 8 valence electrons. So the sulfur anion is going to be sulfur -2. And so it has 8 valence electrons. That is what stable means. And so this is the anion that is of sulfur that is a stable anion. In our next example, it says which ion is the most stable. So when we're looking at this, which one's the most stable? Well, fluorine, chlorine, bromine, and iodine, they are all halogens. In group 17, we just said they have to gain 1 electron to become stable. Well, we're looking at which one is the most stable. Now remember, Coulomb's law is force equals K Q1, Q2 all over distance squared. And so when we're looking at Coulomb's law, the one thing we can think of is which one of these guys is the smallest. They all have 8 valence electrons. But remember that fluorine is incredibly small in comparison to iodine. Iodine is massive compared to fluorine. And so therefore the distance of those outer electrons is greater. So if this distance is a bigger number, the denominator is a bigger number, that means the force is going to be a smaller number. And so therefore the opposite of that, if our distance is a small number, the force will become larger. And that's with the same charge, because in group 17 they all have the same effective nuclear charge. And so therefore fluorine is going to be the most stable because it's the smallest of all of them. So in a question like this, you got to look at what's different. Well, they're all group 17, but fluorine's on the top of group 17, which makes it a smaller anion. Now, an ionic bond. When we're looking at ionic bonds, we really have to think about Coulomb's law. And what an ionic bond is that we have a very strong attraction between a positive and a negative, between a cation and an anion. And we know that when we're looking at this, we have this positive, we have this negative. Whenever we have that, they're going to get at a very short distance, and they're going to be very, very close together and very strong. So an ionic bond forms between a metal and a non-metal. So we're looking at metals and non-metals. Extremely strong bond and requires large amounts of energy to break that bond. The reason why we have that positive and that negative is because what we'll do is we'll have this electron will be transferred to that fluorine. Since fluorine is so electronegative in comparison to sodium, it just rips that electron off, and so this becomes extremely negative, this becomes extremely positive, and they're kept in that chemical bond together because we know that opposites attract. Now, because we have this positive and this negative, this metal and non-metal bond, what we have is in an ionic compound, we have what we call as a crystal lattice formation. Basically what this means is that we have a positive and a negative, and if you look at this, in this, all the positives are surrounded by negatives. And if you look at the negatives, they're surrounded by positives. And so what you have is you have this great attraction for each substance within itself. And so you have all these positives surrounded by all these negatives, and that's why what you'll get solid at room temperature. You have very high melting points and very high boiling points. The one thing that it does have that you kind of got to think about is it's brittle. So basically you can break sheets of it off. And what I want you to think about is if I take and I push on this part of that solid, and I push, and essentially I push this positive down to this point right here. Well, now you have a positive lining up with a negative, and that negative will be pushed down. That negative lines up with a negative, and so therefore you'll have a crack right here. And so therefore they're brittle. They do have high melting points, high boiling points, but they are brittle, and so you can kind of break them into pieces. But to break that bond in between them, to really break them apart and melt them or boil them, you have to put in a lot of energy. So let's look at developing example C1. It says, why are ionic substances able to conduct electricity? So when we're looking at why they're able to conduct electricity, you have this positive and this negative. And when you put them in solution, like we did, what happens is you have this dissociation. And so what happens is your positive and your negatives kind of break up in solution, and so therefore they're able to pass electrons through, and they're able to pass electrons through those negatives to give it that, because it has that positive and negative, and it's able to conduct electricity. Last example, it says, which of the following would be most difficult to break? And so when we're looking at this, we're looking at what would be the most difficult. And we're looking at this one. It says we have our sodium chloride, we have our calcium oxide, and then lastly we have our aluminum nitride. And so when looking at these, what we have to look at is we have to look at Coulomb's law. So Coulomb's law is force equals K Q1 Q2 all over D squared. And essentially all these guys are essentially the same except for what? Their charge. So sodium is going to be +1, chlorine is going to be -1, calcium is going to be +2, oxygen is -2, and then aluminum will be +3, and nitrogen will be -3. And so we have these opposite of charges, and the more charge, the greater the attraction and the more difficult it is to break. So that aluminum nitride should be the most difficult to break because it has a higher charge in that Q1, Q2. So if your numerator is bigger, it's going to take more force.